Okay, we are Utah Valley University. Before I get started though, I would like to thank the NSPS for putting on this competition. This is a great way for students to kind of put to practice everything that we've been taught. Real quick, so I am Sean. I've kind of been voted a little bit as a leader. So we have Derek here, and then Corey, Austin, Mike, and Grant. Well, we did kind of assign roles there and put some names after it. Really, it's kind of just for show. This was a complete team effort. There was nothing done where any one person kind of said, no, we're going to do it this way. From the get-go, even Saturday night, sitting down with our advisor, we did make sure to kind of plan, bounce ideas off of him, bounce ideas off ourselves, and things like that. It did carry into the next day when we got out into the field. Once we knew what site we were going to be on, we kind of sat down together, collaborated, okay, how do we want to do this, where do we want to start, and then kind of go from there step by step. So with that, I'm going to turn it over to Derek, and he's going to start with info we were provided with.
Cool. So we drove out west of Vegas. There was a control point set in the ground. We call that control point 1. Our basis of bearing on the southwest side was north 35 degrees west. This parcel ended up being more like a diamond. So go ahead to the next slide. Our intention, the night before we went out on Saturday night, our intent was to make this thing as square as possible. Before we started laying out our grid or thinking about topography, we wanted this parcel to be as square as we possibly could with a compass. We knew, we've never surveyed with a compass before. We knew it was going to be a challenge and it was going to be a fun thing to do. And so we really talked about our compass technique, keeping each other on line. Then we sought out to provide 1-foot contour topography and produce that in our deliverable. And Corey.
So as Derek said, we wanted to make our parcel as square as we could get it, and so that was our main focus to start out. And to do that, we used the reciprocal bearing method. And so we had a guy on a corner sighting the bearing, and then we had a guy straight down the bearing looking back at us, giving that bearing, so we knew we were online. Then once we knew we were online, we could then run the tape and get our distance off that. And then once we were for sure on our corners, we would check those by doing diagonals from corner to corner so that we could make sure we were square. And if they weren't square, then we would adjust it to make it square. And then once we got it square, then we would then go through and then level the corners, because that was our most important thing. And we knew we had to do topography, so then we wanted to set up a grid. And once we had our grid established, then we could then level our grid shots and get them ready for the contours, and then locate our features from that. And Austin's going to talk a little more about our primers.
Yeah, so we were provided with a magnetic declination, and so we used our compasses heavily for our angles. And so we used our magnetic declination and our true bearing to calculate our magnetic azimuths. And then by using the Pythagorean theorem, we were able to calculate the distances from our center to each of our corners, and as well as, since it is a square, we have 90-degree and 45-degree angles that we can use. And so then we start off pulling our steel tape from our center section, our center control point, straight to the south corner. And then from the south corner, once that was established, we began our traverse, which Mike will talk about.
Thanks, Austin. So like you said, we established our main point was that control point. We traversed south to that south corner, 147.57 feet. And then our first try, we started that. We just started, we used our reciprocal bearing method to go to the west corner. We established it, and then to the north, back to the east, and then finished with our south. and we had a closure of like 1.55 feet. We didn't like it, so we redid it, and we checked a few different bearings, a couple different checks, and we accepted the south corner to be true in relation to our control point. And from that point, we pulled a line from the south corner to the west corner, and note that we were using 100-foot tapes, so we had to go to 100 and then 200 and then 8 more feet, 8.71. And so we pulled two different tapes from the center point and the south point, and to the point of intersection, we set our west corner. And then we use that same method to establish our north corner and then again our east corner. And when we would close the traverse from east back down to south, we ran the bearing in the distance, and we closed with about 0.66 feet, and we accepted that to be square enough for what the method we were using. And so Grant will now talk about our leveling procedure.
So like my team members have said, we wanted this square, our boundaries, to be as close to square as we could. And we wanted something similar with our topography. So we leveled to each of our corners in order to get a secure and accurate elevation on each one. We started with the control point as our backside. We started at the south corner and went around clockwise. The first time, it says there that we have an error of 13 thousandths. And it turned out that the first time we were a little farther off than that, but we'll explain that error a little later. So because we found that error, we did a second level loop, and the second time we came out with the 900ths figure that you see there. And once we were done with our corners, we started with our grid, and Corey is going to talk to us more about that.
Yeah, so after looking at the parcel that we were given, we determined that a 300-foot by 300-foot grid would work for us. It was 50-foot intervals because it was pretty flat where we were, so we figured that'd be sufficient enough for us to use just 50-foot intervals. And once we decided on that, we knew that the parcel, each leg was going to be about 208 feet just because it was an acre. And so we did 50 foot outside each parcel to get a good enough overlap to when we did our calculations for our contours, so we could get the surrounding area and get a more precise contour lines. And then we did our stationing starting at the southeast line from A to G, and so after we got the A through G set up, we then ran our stationing lines perpendicular to that with 0 plus 0, 0 on the 3 plus 0, 0. And Grant's going to talk about how we did our leveling shots for our topography.
So again, this time we did a level, and we did radially so that we could just set up in a few points to catch all the rest of the grid points. We ended up doing this, starting this loop about midway through the staking of the grid because we were a little short on time. But it ended up working fairly well. We were able to split our team into two and leapfrog. We just sent the grid team ahead of the leveling team to conserve some time. And to continue to check for accuracy, we checked back into our corners and into the control point to make sure that we were keeping the exact elevations that we needed for the topography and the corners. So that was the end of the field data, and now Austin's going to talk to us more about the office data.
So once we got back into the office, we know we wanted to calculate the stake plane coordinates, as well as perform a traverse computation. So we did all those at the same time. We used the compass or Bowditch rule for our traverse computation, and we came with our disclosure of 0.66 feet. It gave us a total perimeter of 834.18 feet with the area of 43,491, which is like 69 feet off of a true acre, and then our precision of 1 to 1264. And so we ran those calculations in preparations for creating our map, which Mike's going to talk about.
Yeah, so as we created our map, we had in mind that we wanted to create a professional map that could be used by architects or engineers to design and develop off of. And so we tried to make it as realistic as possible. And so we started with Microsoft Excel, made sure our point file was correct. We imported that into Civil 3D, created our boundary, our site, our parcel, I guess. And then we laid out our grid, assigned our elevations accordingly, and then built a surface and created our 1-foot contour map with 5-foot index contours. And as we did that, we made sure that we did the tweaking and made sure that it was precise to really accurately reflect the topography of our parcel so that it was as best we could get it. We then created, along with our parcel map, the obvious title block, vicinity map, the notes, legal description, to make it as transparent and as real as we could so that when that survey is looked upon again in the future by another surveyor or maybe an engineer, they can see what we did and why we did it, and so they can understand different things. And I will now turn the time back over to Sean to discuss our challenges.
So, obvious challenge everyone's kind of talked about was the wind. That kind of threw us a little bit of a loop. When we're doing a 3-wire level, when we checked back into our first control point, kind of did the math real quick, and it kind of threw a 4/10 bust in there. I was the one behind the level, so it kind of sent me a little bit of a tizzy and angry myself and kicking rocks and everything else. But I decided, hey, let's go ahead and just redo it real quick. So we ended up redoing it, and that's where we got that 9,000. But come to find out that Sunday night when we went back to the office or the hotel, we had a little bit of an error between the person that was calculating the averages for a 3-wire and reading those off to the person who was writing them in the notes. And that's how we found out we actually closed within 13 thousandths. So once we did that, it was like, okay, just redo the traverse, or the, I'm sorry, not the traverse, but the radial loop and come up with our elevations. So we kind of duplicated work, so our kind of pro tip was, anytime you run into a problem like that, just make sure you guys talk it out, just kind of hammer things out and stuff like that. Yeah, check your math. The other thing too, just because we're used to this environment, like let's see, New Mexico and a few others, we were able to kind of watch after each other as far as safety goes and things, make sure everyone was drinking enough and whatnot. Because we are a big group, we made sure not to have anybody off by themselves, just kind of stay together and work as a team. And, I'm pretty proud of all the work that we did. And, well, like the others, we still like each other, so I think we did okay. So with that, I will turn over to any questions that anybody may have.
You were concerned of getting to square your first 4-sided, I guess, irregular quadrilateral. You said you adjusted it to, I'm just talking horizontally now, to square it up. I'm a little fuzzy on how you did that. Did you do that with the compass, or did you do
No, we did that with the chains. So
Okay,
after the first time when we ran just kind of around the loop, we saw how much of an error we had. Then what we did is we just measured back to the first point we did just to make sure that that distance was good. Once that distance, we solidified it. We then ran back up the line again, 208 feet with one tape. And then with our second tape measure, we started at the center control point, shooting a bearing that way, and then just making sure we stayed on line and kind of keeping them, and then just where those 2 points intersected, that's where we did it. And then we're back to the, so that would have been the north point, and then to the east point, and then back to the south. So when we actually came back and checked our distances again to where we started, that's where we came back at 0.66 feet.
Oh, good answer, thank you. So I've got another question too. So you got your grid laid out, now we're going to the topo. So some of those topo shots were sort of intermediate foresights, or did you have a chance to corroborate your topo shots?
They were foresights. Most of them, we set it up to where about every, on average, I'd say 6 to 7 shots just shooting the topo. We were able to hit one of our control point, or the center control point, and then as well as one of our property corners that we'd set.
So some of those topo shots were uncorroborated, but you could tell by just looking at the general overall.
Yeah, but plus, like I said, we made sure to check in multiple times throughout that radial level loop. You know, I think we checked in 8 to 10 times, if I remember right off the top of my head, you know, at various different points between the original control point provided and our corners.
Thank you.
Okay, any other questions from other judges? Okay, from the audience, students, any questions? Okay. That's it, thank you very much.